Okay, welcome to the class, and we started discussing 5G MIMO transceiver chain. Okay, so we'll continue discussing that. There are a lot of things which we need to understand, and we'll try to cover this in next couple of classes. Okay, so this is the idea, and this is where we should look at in the standard. Okay, now I gave you an overview of 5G transmit chain for MIMO. Okay, till up to 4 layers. Right. Okay. So, and what we said was that if the channel rank is up to 4 and base station is transmitting 4 layers, okay, so MAC will send only one transport block to the physical layer which needs to be processed, okay, and of course control information will also come along with that. And then if the rank is greater than 4, then the second transport block comes, okay. We will try to understand why this kind of like architecture is there, wherein like if the rank is up to 4, then there is only one transport block, but if the rank is greater than 4, there are 2 transport blocks, okay, right. We will try to understand that, but before that we are looking at how it is actually done in the standard, okay. So, this is what we know, that maximum MAC layer will pass on either 1 or 2 transport blocks and the related control information to physical layer, okay. Right, so that's what will happen, and so this is basically we understand the 5 MAC interface, and this is what we looked at yesterday. Okay, the 5G transmitter chain up to 4 layers. Okay, and what we are assuming here is that the base station has 64 antennas. Okay, now if you are saying that the rank is up to 4, which essentially means that user at least has 4 antennas. Right, that's when the rank can be up to 4. Right, what is rank? Minimum of NT comma NR. Correct. So if NR is NT, we are assuming it to be 64. So minimum, if the rank has to be 4, minimum antennas at the UE should at least be 4. Correct. Okay. Right. So we started looking at this chain, and what happens, as I said, up to 4 layer. Okay, 5 layer receives one transport block, and this is the transport block which has come, and it undergoes this processing. Okay, this processing we understand completely. We have spent considerable time on understanding it, and then what happens after that is, okay, that this at the end of it we get one modulated code word. Okay, and since it is only one transport block, we call that transport block as index with q is equal to 0. It will become relevant when there is another transport block. Okay, then the index will take values 0 and 1, q will take values 0 and 1. Okay, right. So, and this is the output, okay, which needs to be layer mapped. Okay, and layer mapped is basically what is this layer mapping? How you take this modulated code block and then demultiplex into the number of layers. Okay, right. So what it does is this layer mapping block takes modulated symbol dq of I, the output of the modulated block. If you remember, we discussed long time ago. It's denoted as d. Q means the which transport block you are looking at. In this case, it is 0th transport block. Okay, and I is the running index which denotes the modulated symbol. Okay, so it takes this as input, okay, and then what it gives you is the number of layers. Correct. Okay, right. So and if it is a rank 4 transmission, okay, then what happens? It demultiplexes this modulated code word into 4 different layers. Okay, and we understood what is all this there. So what this new denotes the layer index. Okay, right. There are 4 different layers. Okay, so it will, if it is 2 layers, it will run from 0 to 1. Okay, if there are 3 layers, 0, 1, 2. Because we will have to look at the mapping in the standard in the document which I specified in the beginning of this class. Okay, so what happens here? So you take the 0th from D, you take the 0th symbol, give it to stream on layer 0. You take the first symbol, give it to layer 1. You give it to take the second symbol, give it to layer 2, and so on. Okay, right. So if there are 2 layers, if NL is 2, what will happen? It will be 2i and 2i plus 1, and this will run only from 0 to 1, right? Okay, new will run from 0 to 1. New, so you see these are 2 layers, or these are, in this case there are 4 layers, right? So this is the layer index 0, 1, 2, 3. Look at this, right? And I is the index of this demultiplexed layers. Fine, okay? This is what is happening. So you have gotten 4 layers after that, correct? and this is some notation, number of layers in each, number of symbols in each layer, okay, that is of course equal to, in this case, is M0 symbol by 4. What is this? The number of symbols in, correct, okay, right, number of symbols in the modulated code word 0, okay, right, which corresponds to the transfer block 0, okay. This is how it works. So you have gotten 4 layers, fine, and what happens after that is, since we consider NT is equal to 64 antennas, this chain will have, what will happen after this? There is this precoding, okay. What is this precoding going to give you? Okay, how many physical antennas? 64, and how many layers? The precoder will be 64 cross NL, okay. So you will have 64 outputs after the precoder, okay, correct. So, and then what happens? There is this resource block mapping, OFDM signal generators, CP addition. So this is what we did for single antenna, you will have to do it for 64 antennas. We discussed that in great detail, okay, right. So you see that this is the complexity of increasing the number of antennas, okay. And to understand this better, like the 64 resource block mapping, what happens after that? Okay, so consider that each UE is allocated 1 PRB over 14 symbols. That's just for an example. That's the kind of allocation which is done. Okay, just to show you how it is mapped after that. Okay, so precoded vector, what will happen? What is happening here? The output of precoder. Okay, it is for each resource element. Correct? What are we doing? You are taking 4 layers and you are generating 64 cross 1 vector after that, correct, okay. And where are those 64 cross 1 vector going to go? The output of this, okay. So first element will sit in first resource element grid, second element will sit in second resource grid, third element is going to sit in third resource grid, correct. So there will be how many resource block grids? There will be 64 resource block grids, okay. So that's what I am saying over here, okay. So this precoded vector Vk of xk generated for each REK, okay, and over each RE it's a 64 cross 1 vector because it is a 64 antenna system, okay, correct. So, and what happens? Now look at this, each RE, what does it contain? It contains data for NL layers in parallel, correct, okay. The output, do you understand this? What are we saying here? Okay, because what are we generating? You are basically getting this vector x tilde k, right? V of k is the subcarrier, okay, and x is the number of layers, okay. So you take this, multiply it with the precoder, and you get a 64 cross 1 vector. What is contained in the 64 cross 1 vector is 4 layers, right, okay. So over each subcarrier, okay, right, you are sending data for 4 layers, that's what I am saying. That's what precoding does, okay. You are sending data in parallel. If it is only 1 layer and 1 antenna, what happens? You are sending 1 symbol over 1 resource element, correct, okay. Now what are you doing using this precoding? You are taking in 4 layers and generating 64 cross 1 vector, which you will transmit over 64 antennas, but for over each resource element NL layers are being sent. That's how you increase the data rate, right. That's how MIMO is helping us in increasing the data rate, because you are sending NL layers in parallel over each subcarrier, okay, right. And then of course, now that you are transmitting the data, DMRS will also be inserted in the PRBs. And how many ports DMRS will be inserted? If NL ports, correct, okay. And we see that what is the maximum number of DMRS ports which are defined in the standard? 8 ports. It will become clear. You see this, how many layers we have considered? Only 4 layers as of now. And how many maximum layer I have told you you can transmit? 8 layers, right. So correspondingly only 8 port DMRS is defined. Of course they are coupled together, right, okay. So, and then what happens in this case, just to understand, okay, so this is for, you do this exercise for one user, you do this exercise for another user, right. So precoded data for this precoded data will be for another user will be sent over another PRB, right, okay, correct. So are mapped onto different PRBs in this case. And this flavor of MIMO, okay, just to keep in mind, it is called single user MIMO, okay, wherein the data of each user, whether it's like multiple layers, you are transmitting over different PRBs, okay. This is called single user MIMO. Just to tell you what is multi-user MIMO, this NL layers, right, okay, they could be transmitted to, if it is 4 layers, you could transmit these 4 layers to 4 different users also, fine, okay, right, that can also be done. there is standard allows us to do that also. So in that case what will happen is, so those 4 layers you are transmitting over a single PRB. So each PRB is now transmitting data for 4 different users. So that particular MIMO is called multi-user MIMO. Okay? So in that case that precoder design will become different. That is the only difference. Having understood all this, that's the difference between single user and multi-user MIMO. Okay? So that how do you design a precoder for multi-user case, that's a separate topic in itself. We are not getting into that. Okay? I teach in MIMO course how to do that. Okay? But that's the only difference. Okay? In this case, all these n layers are meant for single user, and we see that the second user, data for second user, we are transmitting over another PRB, which is an orthogonal resource, right? Okay? So what we have studied till now, it is single user MIMO. Fine, okay, and multi-user MIMO is also similar. This NL layers will be meant for NL different users, okay, correct? So that's how it is. Then of course, what will you have to do? This receiver transmitter chain will also will become different, right? Okay, because then you will have to get 4 different transport blocks, because each transport block is meant for a single user, right? Okay, so that design will also become different. I have not taught you that. Okay, but these are the things, it's easy to comprehend once you understand this. Okay, so if let's get back to our single user MIMO. What happens is, you are doing this if you are transmitting NL layers over each PRB. What is happening? Okay, so the total data rate will be how much it will increase? It will be NL times data rate of CISO systems, right? That's because over each PRB you are transmitting NL layers. You are increasing your data rate by NL. Okay, that's how MIMO is one of the use cases of MIMO. We have seen another use case of MIMO wherein you don't need all this when the user is operating at operating in low SNR regime. Correct? User is in a basement of a building. Okay, then what happens? It is fine if you are able to increase the SNR. Right? So what will happen? NL will become only 1 in that case. You will use multiple antennas to increase the SNR, and we know how does that SNR increase? We have studied that. Okay, right? So then, having seen this, what happens after this? You take this is one symbol, okay, right? And how many such resource grids are there? 64 resource grids. So each resource grid is in the digital domain. So you need to convert it to analog domain and up-convert it. Correct? Okay. So what happens after this? So this is, we understood. This is what we have seen for a single layer, okay, or single antenna earlier, okay. What is happening now? So you take this IFFT output with CP, then feed it to DAC. This is the first resource grid. This is the 64th resource grid, right? Okay. So DAC, then up convert, radiate. All of these operations need to happen in parallel, right? Okay. So how many DACs you need? You need 128 DACs. Because for each chain you need 2 DACs. Okay, so if it is 64, you need 128 DACs. Okay, so you need 64 up converters, 64 antennas. Correct? Okay, right? So each transmit chain requires 2 DAC, 1 up converter, and 1 power amplifier. Power amplifier, it boosts the power. Okay, to transmit at a particular power. So similarly at the receiver, okay, so what happens? So each receiver chain, okay, as I said, if it is like you're looking at the user side, let's say the user has 4 antennas. Okay, so each receiver chain will require, you take this antenna, band pass filter, down converter, low pass filter, and then there are ADCs. So this is the opposite of each of the transmit chain. Okay, depending on how many antennas user has. Okay, the number of component is going to increase accordingly. Okay, right? So that's the complexity at the receiver side. Okay, right? So each receiver chain requires 2 ADCs, 1 down converter. Fine. Okay. Now, once you do this at the receiver side, okay, you have gotten back your samples, right? Okay. So now this is the receiver part. Now, what happens in the receiver side again? Okay. So this is CP deletion. Okay. We are assuming that, let's say, user has 4 antennas. Correct? Because we assume that we are transmitting 4 layers, right? So at least 4 antennas user should have. So this is the signal from first antenna, this is a signal from the 4th antenna, right? So what happens after that? Once the signal has been digitized, CP deletion, FFT, right? Then resource block demapping, okay, right? Now you need to estimate the channel also. Okay, earlier also we have to estimate the channel always. Okay, that's why DMRS is being transmitted. We know that now. Correct? Okay, using those 4-port DMRS, channel will be estimated for 4 ports. Right? Okay, you understand how everything is coming together, right? Because what will be the dimension of this? Right? If user has 4 antennas, what will be the dimension of HK? It will be 4 cross 64. What will be the dimension of VK? It will be 64 cross 4. Overall channel is 4 cross 4. Right? And how many DMRS ports do you need to estimate the overall pre-coded channel? 4. So base station will transmit 4-port DMRS. Using that, this channel will be estimated. Using that, after that, the MIMO receiver will be designed. We learned that also. Correct? I showed you SVD based receiver design. We discussed about zero forcing. You take the inverse of the channel, that becomes, right? Depending on what receiver you have implemented, you do this. Correct? Once that is done, what happens? You get NL layers. You get back those layers, right? We have understood that process. You've gotten back those layers. If it is up to 4 layers, you do layer demapping, combine them, right? You multiplex them again, give it back to the rest of the receiver chain, done, right? Okay, so that's what is happening. So this is a system model after taking FFT, right? HK, VK, XK, and this is what we understand. We are very comfortable with this. This is H tilde K, precoded signal, precoded channel, right? Each UE will perform MIMO receiver processing. Okay, any MIMO receiver can be used. We have spoken about zero forcing, SVD. There are other receivers. We did not discuss in detail, but there are other receivers. Okay, correct. And why I have written each UE? Because now UE knows that its data lies in first PRB, second UE knows its data is in second PRB, just for an example, okay, and it goes on like that, right? So if each UE is taking one PRB, base station is doing MIMO transmission for 275 users, right? Okay, and transmitting, let's say, in this case, NL is equal to NL layers, okay, depending on what is the rank of the channel of each user, right? Okay, the decoded data will correspond to NL layers for each UE on each RB, correct? NL layer data you are transmitting, okay. Layer demapping block will multiplex symbol from NL layers into one code block, which is passed on to the rest of the chain. See what is happening here, rest of the chain is oblivious of the fact that it is coming from 4 layers, right? It doesn't care. And then of course the size of the transport block, everything will depend on the NL, but the processing doesn't care. Okay, you'll have to process more number of symbols, right? That is the only difference. Okay, because over the same PRB you have transmitted NL times data. Okay, right? Part of the rest of the receiver chain, similar to the CISO receiver, will process this single code block. Fine. Okay. So this is for NL is equal to 4. Okay, things change when number of layer is more than 4. That's what we are going to discuss. This is rank 8 transmission. Okay, so whatever I am going to tell for 8, it is applicable for rank greater than 4. Okay, so 5, 6, 7, and 8. Okay, right. So if the user is a particular user has rank 8, what happens? Okay, that's what. So what will happen in this case is, recall this MAC to PHY interface. MAC is going to send 2 different transfer blocks. Okay, right. And for the first transfer block, so the rank is 8. Okay, so first transport block will be demultiplexed into 4 different layers like this, same as what we did earlier, exactly the same, because the rank is 8, right? Okay, so the first transport block gets demultiplexed into 4 layers. This is Q is equal to 0. Now you see this. Okay, correct. So and how many layers? 4 layers. Exactly the same operation. Doesn't change, because whatever is happening for 4, it will happen for more than 4 also, to the first transport block. Correct? For the next transport block, same thing happens. Now it becomes, what is the difference between this and this? Q is equal to 1. That's the notation for the second transport block. Okay, right? And what are we calling? See, new now runs from 4, 5, 6, 7, because the index for the rest of the 4 layers. That is the only difference. X4 of I, D1 of I, that's all. Okay, correct? D1 and X4. Fourth layer and the second transport block. Fifth layer, then it runs, it's the first symbol, second symbol, sixth layer, seventh layer. That's all. Okay. So if the rank is 6, then you will not have this. But this will be there, you will not have the remaining 2 layers. So it is not like that it will be 3, 3. Okay, right? So it is 4 and then 2. I think that's what it is. Okay. So number of modulation layer per symbol. Okay. How much it is for rank 8 transmission? How many it will be? M of in each layer, how many symbols you will have divided by 4. Right? Number of layers in transport block 0, right? QPSK symbol you divide by 4, or QAM symbols, and then this is the number of symbols in the transport block 1. So they will get divided by 4 in each layer. So number of layers, this is the number of symbols in each layer, that's all. Okay, for this, when NL is 8, okay, right? Okay. What happens? Again, this is the same example, okay. For this is the transmit processing chain. So what happens? You have first transport block, you have second transport block. Processing is happening. This, whatever you do here, the same processing is happening here. You have to keep this in mind, okay, that the MCS of this transport block could be different from MCS of this transport block. Okay, and because it is, we calculated the MCS, right? Okay, for each layer we calculated the MCS. It is log 1 plus SNR. So this transport block could be seeing different SNR from this. So it is not necessary that both of them will have the same MCS. So you could be transmitting 16 QAM over here, you could be transmitting 4 QAM over here. Could happen. Right? Okay. So both of them undergo this processing. Then what happens? Layer mapper. I taught you layer mapper just now. Okay. What is the output here? 8 layers. Then what will be the size of precoder? Because we are considering 64 antennas again. Okay. That system design doesn't change. Okay. So what will be the size of precoder in this case? 64 cross 8. So each RE now will contain 8 layers in parallel. But this will, how many such resource blocks or grids will be there? 64. That is not changing. Correct? Okay. Whether you transmit 1 layer or whether you transmit 8 layer, if it is a 64 antenna system, you will have to do this processing. If it is 1 layer, then precoder will be 64 cross 1. If it is 8 layer, precoder will be 64 cross 8. But the output of precoder will be always be a 64 cross 1 vector. Right? Okay. Correct? So for 8 layer transmission, physical layer receives 2 transport blocks. Correct? That's what I said. Okay. If it is greater than 4 layer and up to 8 layers. Okay. Phi processes this transport block to give 2 modulated code words with index 0 and 1. Correct? Okay. Layer mapping block takes these modulated symbols DQ of phi from 2 code words as input, and we exactly know how they get mapped onto different layers. Okay, right? In this case, I'm just assuming that as you receiver has 64 antennas. Okay, just for example. Okay, what will happen here? Okay, you are doing it for some system, for some UE, some high-end UE like a laptop. Okay, when it has 64 antennas. Okay, so 64, you take 64 antennas, okay, right, do this processing. What are you doing? So once the signal has been sampled, delete the CP, the FFT, demapping, do the channel estimation, okay, and what will be the dimension of the channel estimates? How many DMRS will be transmitted in this case? 8 port DMRS, right, okay. And using this 8 port DMRS, equivalent channel gets estimated. Then the receiver design, MIMO receiver. Okay, right? MIMO receiver will also see 8 layers. It doesn't care how they were multiplex or demultiplex. you will have this MIMO receiver, whatever the SVD receiver or zero forcing receiver, correct? Once you do H inverse or H tilde inverse, you are going to get back 8 layers. So that receiver design is done for 8 layers, right? Once you do that, then you know what needs to be done after that. You need to demap those 8 layers into how many transport blocks? 2. Correct? Okay? Because that's how you created those 8 layers. What did we do at the transmitter? We took modulated code word from 2 different transport blocks and multiplexed them. Now you are demultiplexing them to generate 2 code words for 2 transfer blocks, and then run the rest of the receiver processing over here, right? Okay. So layer demapping block will multiplex symbols from 8 layers into 2 code blocks. What happens after that? Rest of the receiver chain will process 2 code blocks. Correct? Now this is how it works, but look at the kind of design decisions you will have to take. Okay? Whether you want to, just for example, okay, whether you want to process this chain and this chain sequentially, right? So, or whether you want to basically run them in parallel. Okay, so if you want to run them sequentially, each of them, these blocks need to run at a higher clock, right? Okay, because this chain is waiting, correct? Okay, so whether you want to design a system which is running at a higher clock, or whether you have a system wherein you can have 2 instantiations of these 2 receiver chains. Okay, so 2 instances of receiver chains means what? 2 different, just for example, okay, 2 different LDPC decoders. So whether your device has this kind of LDPC decoder, has space to occupy 2 LDPC decoders or not, right? Okay, so if you are, you pick up a device which can run at a higher clock rate, but which does not give you this kind of memory which can occupy, wherein 2 LDPC decoders can come, right? Okay, so these are the design decisions you have to take in the beginning. Okay, so typically when you architect a system, you look at all this, right, and then design your system. Okay, even here, okay, see what is happening. You can get multiple code blocks over here, right? Okay, then you segment a transfer block into multiple code blocks. You want to decode these code blocks in parallel or in sequence. That's another decision, right? Okay, so you have to, whenever you are designing a system, you need to look at these specifications carefully and then take a design call. Okay, that if it is only for, if the system is designed only for 1 layer, okay, then the system has to be designed accordingly. If tomorrow if I increase the number of layers to, let's say, 16, my current design will not work. Let's say if 6G tries to do that, correct? If this the modulation in 5G is up to 256 QAM, people are talking about 1024 QAM, right? So on each, without MIMO, if it is 1024 QAM, on each resource element you are transmitting 10 bits, right? So whatever resources you had might not work to execute that kind of a processing, right? Okay, and this is, see, look at the complexity of doing it, that the complete processing, at least at the base station side, has to be finished within each slot, correct? If you don't do that, then what happens? Then your system will choke, because you have not processed one slot, other slot has come. Your data is going to overflow, you are going to lose data. So that's a very tight constraint on the physical layer what we are studying. Okay, that entire processing, all this has to be done within 0.5 millisecond in a 5G system. Okay, right? So we'll stop here. We'll continue discussing this in the next class. There's still a few more things which we need to learn about why it is done the way it is done. Okay, so I'll stop here, then we'll continue discussing. Thank you.